I'm going to do, you guys look at any of those questions that I finally got up, practice questions for test 2? Well, they're up. I put 4 sections up, so make sure you start practicing. This will be the next topic, and this is kind of going back to an earlier chapter. But when it comes to atoms, the structure of an atom, you know there's protons and neutrons, and they're in the nucleus. And then around out here is where all the electrons are, just kind of in a cloud out here. And that's all I said before. So we had protons, we talked about neutrons and isotopes a little bit. And we talked about however many protons there are, that's the atomic number. If it has that many electrons, then it's neutral. Metals lose some electrons to become positive. Non-metals gain some electrons to become negative. But the electron configurations, if we look a little closer at the atom, there's a particular structure that the electrons take on out here. So it's just a little more detailed about the electrons and how they structure in an atom. And it's very closely related to the periodic table and why the periodic table has the shape that it does. So this is where we are. I put a lot of these in there, but hopefully by the time you get into these, it starts to seem repetitive. But there's several different ways we represent the electron configuration, meaning the structure out here. But let me give you a general idea of sort of the diagrams we use. And let me just do the protons and neutrons as a little circle there. There's what we sometimes call it a shell or an orbital. It's kind of like, here's the Earth, and here's the moon. The moon's going around out here, so you can picture it that way. But there's a layer here, and then there's another layer out here. There's another layer very close to it, like that. And then we stop there and say, from the nucleus to this first distance out, and then there's another distance out to this next one, and then there's another distance out to this next one, getting a little further and further away. The way I have always done this in early textbooks, they even still have some of the textbooks don't do it this way anymore, but I'm telling you this is the way to picture this. Think like this: 1, 1, 3, 1, 3, 5. 1, 1, 3, 1, 3, 5. Whenever you're about to do electron configurations, first thing say to yourself, 1, 1, 3, 1, 3, 5. And you do this on a piece of paper. 1, 1, 3, 1, 1, 3, 1, 3, 5. I call it the inverted Christmas tree diagram because I just don't see it anywhere anymore, so I made up my own word for it. You've got 1, 1, 3, 1, 3, 5. These are representations of orbitals. And let's say this is like the very bottom. The distance to here is this distance. The distance from the bottom to here is this distance. And then this next one is right here. That's the one that has 3 in it. So that's what going up on this diagram represents: distance from the nucleus. This diagram got really ugly. So there's an orbital here that electrons can be in. That's the closest one. The next furthest out, this one, that's an orbital that electrons can be in. Next distance out, there's 3 orbitals at this next one where electrons can be. And then you go further out, you've got another orbital, 3 orbitals, and then 5 orbitals. All right, let me leave that for now. So next thing you say, each one of these orbitals can have 2 electrons in it. We represent that by going, here's an electron, and we do another electron like that. This is showing electrons pairing. So you probably remember me going, here's oxygen, and here's the Lewis structure, and then these can make bonds. These are paired electrons, and that's sort of referencing the idea that electrons can pair like this. Electrons, they actually have a magnetic property instead of the positive, negative electrostatic attractions that we talked about. And that's why we represent them like this. It's a north-south of two magnets will stick to each other. So if I had a bar magnet and another bar magnet, I would flip them like that and then they would stick like that. So you can kind of picture it that way. There's a magnetic property that makes them pair. And that's really all I'll say about the magnetic property, but just realize they pair. That little set of facts makes this very easy. So this is one way to represent an electron configuration, and I'll show you how you build that. It's actually very simple. If you'll do this, I swear, if you will do this, sketch that on a piece of paper, 1, 1, 3, 1, 3, 5, the rest of this is very easy. But this, just realize this is what it represents. This is the closest orbital, this is the next closest orbital, this little set, they're all equidistant here. But this little set of 3, that's the next closest orbital. Right. So let's do, I should have brought periodic tables. I'll bring up a periodic table. If you're watching the video, bring up your periodic table. Okay, how many valence electrons does oxygen have? It has 6. So we'll do oxygen, 6. Okay. If you will do this, oh, I better do something else first. The way I grouped this, there's 1, 3, and there's 1, 3, 5. So let me put some labels on these. These are just by convention, we have certain labels we use on these. This first one here, the single ones, the ones that are by themselves, the ones, the one, we call that an S orbital. The ones that have 3 are called P orbitals. So I'll put a P here for each one of these. These are just historically by convention. This is what spectroscopists came up with as labels. So it's called S and it's SP. The ones that have 5, this one has 1, this one has 3. The one that has 5 is called D. I should be using lowercase. By convention, we use lowercase. So it could be A, B, C, D, but spectroscopists had a reason for doing this historically. This meant singlet, this meant plural, and then they figured out single and plural isn't all there is to it, so D meant diffuse, but just memorize SPDF. There are more up here. There's 1, 3, 5, 7 next, but and then there's another one, 1, 3, 5, 7, 9. So 1, 3, 5, and then 1, 3, 5, 7, and then 1, 3, 5, 7, 9. But we won't get that far because things get really weird up there, and we get into the transition nodes. But the more simple ones, okay. So there's this, and then there's the 1, 3, and there's the 1, 3, 5 getting further and further out. This is called the first shell. We'll do some orbital theory and we'll call it n equals 1. But this is the first shell, and it only has this one orbital. This is the second shell, so this is the 2s, 2p, 2p. So that's the labels for these. And then this is the third level, 3s. So again, this is just by convention what we call these. And these are the 3d orbitals. And things do start to get weird further up here, meaning the first, I've got 1s, 2s, 3s. I would think I would go 4s, and then 4p, and then 5 4ds, and then there's actually 9 4fs. But I'm really going to stop here, but I do want to just say one more thing. This is one of the things that gets weird the further out you get. The 4s is actually closer. The 4s actually shows up here. So let me erase those because we're not going to go up that far. And let me get a little more distance on the 5. 3D. I just want to sketch in the 4s here just so you be reminded that it's there. That's where things start getting weird. But if you remember 1, 1, 3, 1, 3, 5, maybe you can remember the 4s's right there. If you can do that, then this is very easy. So there are the labels. So you go 1, 1, 3, 1, 3, 5. Maybe you can remember that this little aberration is here. The 4s starts here. And then you get the 4p up here. So let me back off the weirdness and show you what's simple. Okay, so you got the labels. If you can get this sketched out on a piece of paper, the rest of this is very easy. I said how many electrons are in a, I said valence electrons. How many total are in oxygen? And we're talking about the neutral atom.
8.
It's 8. So the 8 on the periodic table tells you that's how many protons it has. But for the neutral atom, and that's what I'm talking about here, that means it has 8 electrons. Video. So oxygen actually has 8 electrons. 8 electrons total. And this is how you make the electron configuration. You start down here and you count 8. 1, 2, you pair them and you make sure you just make an arrow going up and an arrow going down. Actually, we use half arrows by convention. So you go 1, 2, you come up here and you go 3, 4. Now when you get to some that are straight across, like these and these, or you've got several straight across, now you fill them singly. So I'll go 1, 2, 3, 4, 5, 6, 7. Now I'll go back and start pairing 8, and that's it. That's the electron configuration of oxygen. When you're in these single orbitals, you go 1, 2, 3, 4. When you're any of these that have several orbitals at the same level, you fill them up one at a time, and then you go back and pair them as you go. So let me do it again, following those rules. You look at the periodic table, the atom we're doing has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. That's the electron configuration of oxygen. And it really is that simple. If I said something else, what else could I randomly pick? Let's do one more row down. Let's do phosphorus. How many electrons does phosphorus have? It has 15. If I did phosphorus, which has 15, I would go 1, 1, 3, 1, 3, 5, and then I would label things. And now I need to count to 15, so I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the electron configuration of phosphorus.
So you said this is the ground state like diagram?
Oh yeah, some books say it's the ground state, but because we haven't talked about orbitals and any spectroscopy, you don't know what to compare that to. But this is the ground state, so just kind of a hint about what ground state means. A photon of light comes in and hits an electron. One of these can pop up here. That's not the ground state. That's an excited state.
So how would you write the electron configuration of that? Would you just add
of the ground state?
No, of an excited state.
Well, I'll get to how you do this. Write this differently.
Okay.
And you could write that differently, but that's getting ahead of things. Kind of the last thing we'll do this semester is the orbital stuff, because it's not very intuitive. It's quantum mechanics and it's all kind of weird. But for now, just think we're doing ground states. There's kind of nothing to compare ground state to. Okay, electron configuration of phosphorus. You with me? It is that simple. If you can go 1, 1, 3, 1, 3, 5, and then get the labels in, and then you just count up following those rules, you've got the electron configuration. You with me? Here's the thing, there's more than one way to represent an electron configuration. This is my favorite way, this diagram. And this is where I tell you to start. because it is that easy. But here's another way to represent the electron configuration for phosphorus. Phosphorus. 1s, and there's 2 electrons, so we do a superscript. And then there's 2s, and there's 2 electrons, we do a superscript. And then there's 2p, and there's 1, 2, 3, 4, 5, 6, so we'll put 6 there. And then we've got the 3s, so I'll put a 2 there because there's 2 electrons. And then we get to the 3p, we've got 1, 2, 3. That's just a different way to represent the same exact thing. It is that easy. So don't let electron configurations confuse you. These should be kind of easy on the test. Another way we can represent this is, if I did the electron configuration of, I'm doing phosphorus now. If I did the electron configuration of, say, neon, we would fill this, and then we would fill this, and that's where we would stop. There wouldn't be any electrons up here. This S and P together, there's 8 electrons here. This is that octet we're always talking about. When it's the S and the P's, the S and the P's, and this 4S and the 4P's, when those are filled and then nothing above it, that's that state where it's got 8 electrons in its S and P orbitals. That's that octet we're always talking about. So another way to represent this is, let me do this. 1, and then 1, 3, and 1. 1, 3, 5. All right. If you look at the periodic table and you look at the right side, those noble gases, the electron configuration of helium, it's got 2 electrons, so that's its electron configuration. Next is neon. I'll also do argon. How many electrons does neon have? You look at the periodic table, it says 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the S and the P is full. Here that 1s is full. Here the 1s is full. There's no more above there. Here the 2s and the 2p are full, and then there's nothing above there. And argon is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Again, it's the S and the P that are full. And there's a particular sort of stability an atom gets when it has the S and P full and then nothing above it. So what I'm getting at is, when I did phosphorus, look here at phosphorus. I did phosphorus, but that's 15. If you go down in the numbers, down 12, 11 to 10, there's neon. Another way you can represent this is neon is 1s, neon is 1s2, 2s2, 2p6. That's the electron configuration of neon. And that shows up as part of this one. This was for phosphorus. So another way, here's one way to represent the electron configuration of phosphorus. Here's another way to do the electron configuration of phosphorus. And here's one more, it's just a summary way. We do this, we put neon there, and that represents that much. And then we add the rest. 3s2, 3p3, there's another way. So now I've showed you 3 ways to represent the same thing. You with me? This is the easiest way to get it on a piece of paper. And then from there you can just peel out what you've got here into this, or you can do this if you needed to. That's up to here is the construction of neon. And then 3s2 and 3p3. So that's another way to do it. I didn't see this in your book, but most books do this. A 4th way to represent it. 4th way to represent it.
will you accept anyway? Like,
The question will indicate which one. Since I do multiple choice, it'll be right in front of you. But books like to do this, and I think the ACS test does this. But here's another way to do it. 2P, 2P, and then 3S. 3P. Actually, the 4S starts here, covers some of that. We would do the 4S next. And then to represent the electrons, you just do this. So here's phosphorus again. Yes, and then all of these are full. Or we get to the 3S. So there's a fourth way to show the exact same thing. Sorry. So for the video, this is the fourth way. You make a box for 1S, you make a box for 2S, you make a box with 3 boxes connected for the 2P. It really is that simple. I think I need to sketch the periodic table. Let me do that real quick. But remember, when you're doing electron configurations, the first thing you do is say to yourself, 1, 1, 3, 1, 3, 5. Construct this. Hydrogen. Helium, transition metals, Mg transition metals, fill those in. Help so I don't have to keep flipping the camera back and forth. Here's the transition metals across here. Did I get 10? 5, 6, 7, 8, 9, 10. That's 10. See, I've got helium in the wrong place. 5 more. that's kind of a sketch of the periodic table. All right. The periodic table is really has this shape because of properties. All of these have similar properties. All of these have similar properties. It turns out helium just belongs over here. But notice the weird way that this is constructed. If I took helium off here, and I just kind of sketched it in over here, this will make more sense. But look at the periodic table and look at the way the 1, 1, 3, and 1, 3, 5 goes. One, 3, 3, 2. Oh, and when you do this, there's 1, and then there's 1, and if you line that up with the center one of the 3, it keeps it kind of neat. So I've got the center one lined up here, I've got the center one lined up here, the 5 has 2 on this side, 2 on this side. That'll help you if you just kind of keep it neat like that. Okay, filling the first orbital. There's the electron configuration of hydrogen. That's the electron configuration of helium, but I've cheated it back over here. That's the first shell full. Next, that's the electron configuration of lithium. It's got 3 electrons. Beryllium has 4, so now we're filling an S again. 1s, 2s. So these 2 are here, these 2 are here. This block is called the S block. Do you see why it's called the S block? These 2 rows here are the S block. Let me keep going. I just filled these 2. Now I'm going to fill the 3. 2, 2, 2 at 6. There's the electron configuration of boron. There's carbon. There's nitrogen. There's oxygen. There's fluorine. And then there's neon. The S and P is full. 2p, 2p. S and P is full. That's what is kind of a hallmark of these. So as I fill across these, that's why this is called the P block. You see why it's called the P block? So this is giving you a hint as to why the periodic table is constructed the way it is. But really it's constructed this way because of properties, and it turns out the properties have everything to do with how these configurations are. So now I did the neon. Now I come back over here and look where I am. I'm back to S. 1, 2, 3 down. We're at level 3 here. This is the 3s we're filling. There's sodium, there's magnesium. Now we're back over here to aluminum. That's the electron configuration of aluminum, silicon, phosphorus that I just did. There's sulfur, there's chlorine, and there's argon. And look, S and P full, 3p, 3p, 3p. So now we're all the way to argon. All right. This is called, as you might imagine, the D block. But notice we're actually here on the periodic table next. So potassium and calcium. Potassium, K, calcium. Remember I said that the 4s really starts here? It's just it breaks that neat pattern, 1, 1, 3, 1, 3, 5. So I kind of leave it off. But this is actually where the 4s starts. And if you forget this, what's weird about right here, you just look at the periodic table. If you go across and start filling this up, you realize you get back to the S block before you get to the D block. So the configuration for potassium is that. Put a little electron there. For calcium, it's that. So that's the electron configuration of calcium. There is a 4s there. Now we're to the D block, which is this. We start with vanadium, scandium, titanium, vanadium. This is where I'm going to stop. Titanium, vanadium. So of course, you can probably predict what's going on. Here's the configuration of scandium. Here's titanium. here's vanadium, and I'm really gonna stop there because things kind of get weird here. These are so close in energy, the 4s and this, that things get weird, so I'm just gonna stop there. But you see what's going on. So, periodic table configurations, electron configurations. So it gives you a hint as to why the periodic table is constructed this way. It also tells you, I'm going to put helium back over here where we usually put it, but helium is technically part of the S block. So helium's weird, but back over there. But the S block, you're always filling an S. The P block, you're always filling a P, and then there's nothing above it. And then when you get to the D block, you start filling that, and there's nothing above that. But you see this 1, 1, 3, 1, 3, 5 that I told you to always start with? If you've got a periodic table, and you always do for tests, and hopefully have one in front of you when you study, you can get the rest of this. I mean, what do you think goes next above here? I mean, if you go across on the periodic table, you do find out that there's a 4s here. Now we go to the 3D, so you know this is 3D. 3D. What do you think is next? Well, we're here, so what do you think is next? We're in the P block, and there's no P's here. We've got 2P here, 3P here, so this is going to be 4P. So 4P is next. 1s, 2s, 2P, 3s, 3P, and then we actually get the 4s here. And then we go to the 3D, which is here. And then we hit 4P here. And then we go over here. Now we're on 5s. So my point is you can actually get the rest of this just looking at the periodic table. Except for the weirdness of helium. You can see that you start with the 1s, and then that's it for the first level. Then you get 2s and 2p. Then you get 3s and 3p. Then you get 4s, 3d, 4p, 5s, 4d. You see what I'm saying? So you can get all of this construction. It starts getting weird here. This pattern starts to break down. But it is true that in the first level there's only s. In the second level there's s and p. In the third level there's s, p, d. In the fourth level there's s, p, d, f. I just cut it off my periodic table. I think no, it's down there. We could squeeze these along here, in here, and make the periodic table way longer, left to right. But chemists just go, okay, that makes this diagram start to get ridiculous. So there's a little note here that says, oh, you go down here and you start filling these. So you could get the F orbitals too, which is going to, instead of 5 across, it's 7 across. 1, 3, 5, 7. Yeah, 1, 3. There's 1. There's 1, 3. And then there's 1, 3, 5. And then the 4 is 1, 3, 5, 7. It does go on, but we almost never talk about the atoms down in here, below about the 4th level, except for maybe some of the stuff like gold and mercury and stuff. But that's because those are so rare that we just never, very rarely deal with stuff like that as chemists. So you follow this? So it is related to the periodic table. So let's look at some of these exercises. The book, electron configuration, the full electron configuration. Oh, there it is, orbital diagram. That thing with boxes. Etc. This is orbital diagram. But I'm going to do things as multiple choice. So you'll see which one of these different ways to represent. Let me look real quick in the chapter and see what, I thought I didn't see the boxes. How electrons occupy orbitals. Yeah, I guess I better say something about that one. Yeah, this one gets into orbital theory. I think 3-4 is where I want y'all to be. Little diagram. Let's see what they mean by orbital diagram. 45, 46. Electron configuration, electron configuration. Orbital diagram is just one of those different ways to represent things. That's 47. Chapter 3. Chapter 3. Was it 47? Chapter 3, chapter 4. Almost there. Hold on. Oh yeah, they're doing the boxes. I swear I didn't see that in the chapter. But... All right, go back. 4 exercises. 47. No, it's chapter 3. Sorry. So 47 and 48 ask for the diagram. 49. So this is just an exercise to do all. Yeah. Maybe I should just, that's kind of excessive. 49. 50 is fine, electron configuration of vanadium. Maybe I should take that one out too, because they're getting to the weird things. And when you get to the transition metals, the D block, things go a little weird. I'll come back to that, I think. Tim, I think you can do 51 and 52. All right, so let's go back to 44. Let me do 46. I better keep this here. I kept it. Argon. Leave that there. What number are we on? Around 46. Okay, look at 46. Everything except for my sketch of the periodic table. Again, what we're doing can also be called the ground state electron configuration. Ground state electron configuration. Okay. You're doing homework, you're taking a test, and it says give the electron configuration. Electron configuration is 1s2, 2s2, that form, and then orbital diagram. That's when you do the boxes. 2s. So this is asking for electron configuration. 1s to 2s. All right. What is it for nitrogen? What do you do first? Say it out loud. Huh?
1s2.
Yes, but what do I tell you to think?
Oh, there's a Christmas tree thing.
And what do you say to yourself? I'm telling you. What do you,
1, 1, 3, 1, 3, 5.
think to yourself, 1, 1, 3, 1, 3, 5. And that'll remind you to go, oh, yeah, okay. 1, 1, 3, 1, 3, 5. Something goes right here, though. What is that? 4S. 4S goes there. Just remind yourself it's there. So you got 1, 1, 3, 1, 3, 5. What do you do next?
5 nitrogen.
You need a number in your head. You find nitrogen on the periodic table. Periodic table. There's nitrogen. What's the number? 7. Meaning it's got 7 electrons. And now you follow those rules. And you count to 7. 1, 2, 3, 4, 5, 6, 7. That is the electron configuration of nitrogen. But to write this out, the 1s2, the 2s2, we need the labels. So what's the label that goes on these?
Oh, 1s.
Well, it's S, the ones I was pointing at. These are the S. The ones that are 3 are P's. And then these are D's. D, D, D. My ugly cursive D. Now we number them. What's the number goes here?
1.
So that's the first shell. So these are 2. These are called shells. So this is a number 2 shell. And then it's subshells. So the 2S is a subshell of the second level. And then these are 3S, 3. And now that you've got the labels, whether you want this form or this form is very easy. 1s2, 2s2, 2p, 3, and that's it. You could also do this as, we replace the 1s as helium, but it really doesn't make it shorter here. 2 different ways you could represent. Really, there's 3 different ways on the board that you could represent nitrogen. There's this, but books have quit doing this, but I just think that's the most intuitive way to think about it. There's representing it this way, there's representing it this way, and you could also do It really is that easy. I'm telling you, start with this, and then the rest of this is just easy. Let's do, what if we did sulfur? What's the number for sulfur? 15. If it's 15, you're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's sulfur. Is it 15?
16.
16, so there's one more. 2, 4, 6, 8, 10, 12, 14, 15, 16. There's sulfur. Let me show you one more thing. Let's do side by side. let's go down the periodic table, say, for, what should we do? Let's do hydrogen, lithium, and sodium. Hydrogen, lithium, and sodium.
Okay, we're getting crazy. I said we're getting crazy.
Oh no, getting crazy. All right. That's the electron configuration of hydrogen. Just one. Here is that's lithium. And that's sodium. Almost put S for sodium. Do you see something in that? Every one of these has one electron. Its outermost electron in an S orbital. You see that? I've got a periodic table on the board. Why do I do that? Okay, so that's kind of the point I'm getting at. If it's an atom that has one electron in an s orbital, they're all going to have very similar properties, whether it's ionization or if it's a non-metal, then it's how its bonding behavior is. But you see what's similar about them. If we did next, let's do helium. Sketch it in over here. Helium, beryllium, and magnesium. There's helium, there's beryllium, and there's magnesium. Those all have similar properties because it turns out properties come from this structure. This has 2 in the s orbital, this has 2 in an s orbital, this has 2 in an s orbital, with no electrons above them. If I continued with this, I guess I have to go to, so once this is full, I have to go to lithium, boron. What if I did boron, carbon, and I will put aluminum. So boron, aluminum, and what is below aluminum? Gallium. Let's try to do these. I should stay away from gallium because there's some weird rules that start to occur as you start to fill up these. But let's see what happens. All right, boron. 1, 2, 3, 4, 5 electrons. 5, there's boron. Aluminum. Do you need the periodic table for those numbers? Boron, there's 5. Aluminum, 13. 13. Gallium is 31. It's 5. So let's do aluminum. That's 5. Now we need to do 13. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. 4s is here. And then 4d is next. And gallium is 31. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 1, 2, that's 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. So the 2 and the 4s, that makes 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and look again. You got the S full, and you got 1 in the p orbital. You got the S full, and you got 1 in the p orbital. You got the S full, and You got one in, sorry, these are P's. And one in the P orbital. So I just wanted to go through that exercise to show you that there's something similar about these electron configurations of atoms that are in a column. You with me? I don't think I need to do more of these. But let's just do these. Sulfur, neon. I'll leave those there. Neon. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for neon. If you do neon, you'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Neon is one of those noble gases, but notice that's the S and P full. All the noble gases are like that. The first one, helium, because there's only one subshell in the first shell, completely full is just 2 electrons. But by the time you get to the second shell, you have an S and a P, so that's why neon is like that. If I did next argon, we would be that's argon with the S and the P full, with nothing above it. The next one, try to do that. My 4S there. If I wanted to go to krypton, I did argon. Once you get to krypton, you're going to go across one of the d orbitals. Krypton is 36. Krypton is 36. But I can do it without counting to 36. There's the S and P. The S and P full. The 4 S's right here, but there's nothing in it for argon. This is what I was saying, kind of gets weird because we've got this 3D orbital in the way. But if we count it up to 36, it's going to be the S full and the P full. S full and the P full, and no more electrons above it. S and P full, no more electrons above it. S and P full, no more electrons above it. And then hydrogen, if I wanted to continue here, hydrogen is just, helium is just an S1 S full. Helium, neon, argon, krypton. S and P's are full, except for the exception is helium, where it's just the one S. See what I mean by the S and the P orbitals? If they're full and there's nothing above them, you're on the S and P full. Potassium, right here. The number is 19. Two, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, that's the 4S. 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. If I wanted to write it out, this is potassium. I would go 1s2, 2s2, 3p6, 2p6, 3s2, 3p6, 4s2, no, 4s1. That's where we are. We're in the S block with one electron. You could write it like that. You could also write it as, here's potassium. If we went back to argon, so argon is 3s, 3p, 4s. Yeah. Up to there is the configuration of argon. So I can use argon, do it that way. I could also draw all the boxes. You guys okay with this? So electron configurations. I'm going to leave it at that for the electron configurations. But it is easy if you go 1, 1, 3, 1, 3, 5. And you just start there, it gets you started. You could use the periodic table to finish them out. And make the full Christmas tree, inverted Christmas tree. And you could get any electron configurations from it. But like I said, I've skipped a little discussion here on some weird stuff that happens. Probably come back to it, but. The next topic is going to be kind of picking up here. Okay, we did some of chapter 8 for test 1 and a little bit about reactions. I want to do aqueous solutions and solubility. There is something kind of simple about this too. If you take the class from me, because I always give you this, right here. Use table 8.1. Just know how to use it. And then this is actually very easy. How should I do this? I started a test 1. Test 2 PowerPoint. I will upload this, but so far all I have is table 8.1 in it. So it's just a chart of ionic compounds, and it tells you how to decide whether something is soluble in water or not. Solubility here means in water. There are other liquid solvents that you can dissolve things in, but this chart specifically says compounds in water, and that's all I'm asking you to look at. The way to use this chart, compounds containing the following ions are generally soluble. And then there are exceptions to the rule. Let's see, exceptions. There's four ionic compounds that contain chlorine. Back and forth here. So these contain chlorine, and if I ask you, is this soluble in water? Is this soluble in water? Each one of these, which of these are soluble in water? You look at this chart, table 8.1, and you see chlorine on the left here, third entry down, chlorine, bromine, iodine. It's telling you that in this column, it's telling you these are always soluble in water, except the GCl, H2 is one of those polyatomic ions, Hg2, charge 2 plus, H2. One more. We skipped it though. It's telling you that these are the exceptions. So these are not soluble. And these are soluble. You see what I'm saying? How I'm using that chart? Anything with chlorine in it, any ionic compound with chlorine in it, is soluble in water, except a GCl, Hg2Cl, and lead-Cl. That's how you use the top part of this chart. You guys follow that? Those of you who haven't looked at the screen, these are the ones that are not soluble. Anything else is soluble. Anything else with chlorine is soluble. And same with bromine and iodine in that chart. Go back to the chart. So that's how you use the top part. The bottom part says these are not soluble. That's missing some entries. Well, just look at the OH and the S2, the OH and the S, and the CO3 and the PO. They've got something missing here. I'll have to find a chart from another book. By the way, I will not use this book next semester. I'm going to go back to the book I'm used to. This one is particularly bad. I'm not the only one. Another instructor that started with me this semester, we both just took this book and read it. So this one is saying, let me do this. Anything anything OH. Must have bored into that. Where am I? So anything with OH. OH is another one of those polyatomic ions. So OH was in that list of polyatomic ions. And it's one negative, so you can have NaOH, LiOH, NaOH, KOH, I'll stop there. You can also have beryllium OH2, Mg, OH2, I might just those are soluble. Yeah, the weird way they did this chart. But in this chart, I see why this chart's confusing me. All right. These are soluble. Generally insoluble, Exceptions, okay. That's not the way to do this chart. I will bring a better chart Wednesday and we'll pick this up. We'll use a different chart. Look closely. All right, let's just stop there. We'll start this Wednesday. Let's see if you can do electronic configuration. They are pretty easy.
Is there a place I can go to